All right. So listen, like I said, we should have been starting this unit 7 school days ago, so like a week and a half ago. That's where we're at. So we gotta work to make up time. I don't want to split this unit over the Christmas holidays if we can avoid it, right? So we're gonna try and push our way through it. I might have to pull a thing or two out of it, which is unfortunate, but where we're living. So today we're gonna jump in on lesson 4.1, and we're calling this Equilibria. Right? And what I want to do today is imagine a simple reaction. The burning of hydrogen gas. Obviously, what is that reaction? Who can tell me the chemical equation if we are burning hydrogen gas? Yeah, we would have H2, obviously. Oh my. I'm in jail for this guy. Thank you. Microsoft. Did you say something? So, yeah, this is Microsoft. Please accept. There we go. Okay, so imagine a simple reaction with burning hydrogen gas. We have hydrogen gas reacting with oxygen gas, right? And it's going to yield us what? H2O. And this obviously isn't balanced. How would I balance it? Sorry? Yeah, we could do that. I'm going to put 2s here. I don't actually, it's fine. It's allowed. I don't love the half balancing, but it certainly would be correct. That's a real reaction, right? Okay. Is this reaction a positive or a negative delta H? Just out of curiosity. You don't have to write this even. I just want to see what our memory. Burning hydrogen. What do we know about that?
It could be positive.
You just said both.
Positive.
Okay. Would it be positive? That would mean that this absorbs energy. Do we absorb energy when we burn? Famously, when hydrogen explodes, everything around it gets colder?
No, but you're giving it energy.
You're giving it energy, which means that's the activation energy, but does it keep that energy?
Oh, so it's negative.
Yeah. Again, you don't actually, this isn't actually part of the note. I just want to make sure we remember that, right? It releases heat, right? You can put that. I'm going to put it here. If we wanted to, could we write a rate law for this? We could write a rate equation for this. And it would be what? Absent, we don't know if this is one step or multi-step. We don't know K. We're not going to do an experiment to find it. So we're going to have to use some letters here, but that's okay. What could we say? We could say that for this reaction, the rate would be equal to what? Well, what should come first?
Okay.
Some constant K, right? And then times the concentration of H2, right? To some exponent. I'm just going to put an M there. Whatever. And then O2 to some other exponent. I'm going to put a P there. I don't know. Okay. Does that make sense? Okay. As it happens, this is a pretty fast reaction, right? In grade 9, you did this for sure. Probably in grade 10 probably in grade 9 as well. In grade 10, In grade 9, we produced hydrogen gas, usually by mixing magnesium metal with hydrochloric acid. It bubbles up, and then we did a test for it. Does anyone remember what test we did for the presence of hydrogen gas? We put a splint in, a burning splint in. What do we observe? Nope, that's oxygen, right? Because oxygen makes the flame burn brighter. It exploded. And there wasn't so much of it that we got a big, like, whoosh. It was just a little bit, but it happened so fast that all you really probably experienced was a poop. Remember that? A little poop. Do you not?
I didn't do any experiments very long.
Really?
One second. Is he just gonna come out with a bomb? What the hell? What is he getting? I'm scared now. I'm ducking under my desk. It's so fast.
Can somebody grab me a lighter? Do they know whether they're in the back? Does anyone know where they are in the back? Lighters? Somebody grab me one.
Mr. Michael, what letter is that on your screen?
P?
No.
You know, you guys criticize me a lot, but that one I think kind of just looks like a P.
It looks like a P, but I thought it was like an R and like an. I thought
Like
it was
some
one of
Greek
these-
letter? Were you thinking it was some kind of weird Greek letter?
Yeah, that's what I thought it was.
That's fair.
I genuinely thought it was.
That's fair.
Yeah, that's kind of weird.
Okay.
Yeah, the M
Okay, so this, you know, just, again, a lab that you probably did at some point, but if you didn't, might as well see it. We can take some magnesium metal, and magnesium will react with hydrochloric acid to produce what? Magnesium chloride and hydrogen gas. And if you look, you can see that right there. We're getting a good amount of hydrogen gas produced. You see all the bubbles? So I should be able to, we know hydrogen gas, of course, will react with oxygen, just like this, right? If I had enough of this, you could cause a serious problem. Perhaps you've heard of the Hindenburg, the famous example of hydrogen gas reacting with oxygen. Have you not? I'll show you a video of that after. But I can introduce some activation energy in the form of heat, which is all this is. It's just activation energy. It's just heat. And listen, hopefully this has gone long enough. Settle down. There you go. A little explosion. But note how fast it happens, right? That reacted so quickly that we didn't really have time to, you know, observe any fire. There was fire if you had a high-speed enough camera, but that reaction just happens really fast. I'm going to cap this up because you get another one at the end.
I was able to.
That's so close to it.
Did you think it was gonna explode on you?
No, I was not prepared for that.
I thought the glass was gonna explode. I thought that's what was gonna happen.
No, I was
I'm
looking at the test tube. I didn't know that there was a sound coming.
A lot of these don't work. The first one he picked up, it just happened to work. No, genuinely, we just got real lucky. Okay, guys, stop playing with lighters. Let's do a shirt. And put that down. Every time you chop it up,
Yeah, we'll see if we can get another good one out of that when we're done. So, this reaction happens fast. If we were to kind of make a diagram of it, right? We are releasing energy. So is it going to look like this, or is it going to look like that? That? Yeah, you're right. So this particular reaction looks like this. We start with H2 and O2, right? And really quickly, we end up with H2O, right? So steep curve equals fast. Does that make sense?
Wait, so the product was just water at the end, like in the tube?
Yeah, you can actually see it on the sides. It starts to condense once it cools down. And a bunch of it obviously would have ended up out here. Yep, just water.
But I swear I heard you say you put like magnesium. What happened to that?
Well, that's just to make the hydrogen, right? Different reaction. The magnesium is reacting with the hydrochloric acid. You don't need to write this. Don't write this. It'll seem like it's coming out of nowhere. To make magnesium chloride and hydrogen gas. The hydrogen gas reacts with the oxygen to give us water. Yep. Does that make sense?
Oh, okay. That makes sense.
Cool.
The hydrogen.
Yeah, I just had to do this because I don't keep like a big jar of hydrogen in the back. No. I'd like to, but yeah, they're weird about that. But here's the thing. Let's consider another reaction. I probably did this one with you in grade 9 if I had you, which is you can take water, and if you just plug it into a battery, if you give it some electrical energy, you can split it into hydrogen gas and oxygen gas. And you can do this with liquid water more readily than gaseous water, but I'm just going to keep it this way to be consistent, if that's okay. So you can break water up into hydrogen and oxygen. That's a real reaction. What do we notice about that reaction relative to the previous one? Sorry? It's the opposite. What would the rate law for this be? We can write a rate law for this. Yeah, and it would be the rate is going to be equal to some constant. Now we got to differentiate that these are different constants. I'm going to call this first one K1, just arbitrarily. I'm going to call this one K2, just to show those aren't the same constant. Does that make sense? Bless you. That's important to keep in mind, right? When we say a constant, it doesn't mean the same constant. And in this case, the concentration of water to some exponent, I'm going to use M here. You use whatever you want. Doesn't matter. Yeah. Did I? I think I used N. Oh, I used N. Let's use N. Yeah, I'm just going to use a different one. It doesn't matter what it is. I'm just picking random letters here. If we did the experiment, we could find the actual numbers, right? This, as it happens, is a slow reaction. But it does happen. Now, since we're surrounded by water everywhere, why doesn't all the water around us break down?
Because there's no electricity.
Well, but there's energy. There's energy. There's sunlight. So there's enough energy. This reaction happens. In fact, we shouldn't even put electricity. We should just put energy. You need some kind of energy. Electricity will do the job, but enough activation energy will do the job. So this reaction absolutely happens. And it happens according to the rate law. Rate equals K times concentration of water. The concentration of water on our planet is really high. We got water all over the place. This reaction does happen. Now, it's slow. But even though it's slow, it's happening. And the concentration of water is enormous. So it should happen as quickly as it's going to happen. And the Earth's been around for billions of years. In billions of years, surely our water could turn into hydrogen gas. But we still have water and it hasn't all turned into hydrogen gas. Why?
Is that not like evaporation?
Because it's like stable, so it doesn't have to like break.
That does happen. The reaction does happen. Water does break down. So why aren't we surrounded by big clouds of hydrogen gas?
Maybe it happens, it breaks down, and it converts back to water.
Because both reactions happen. Does that make sense? Both of these reactions happen. And the first one happens more quickly. So we could look at it like this. Let's imagine, if we may, that we use red to show the amount of the amount of hydrogen gas and oxygen gas present. And we're going to use blue to show the amount of water present. Does that make sense? Mm-hmm. All right? And on the bottom here, we're just going to say time. All right? No unit. The unit doesn't really matter. If we start off with a bunch of hydrogen and oxygen, what's going to happen to it? Well, it's going to get used up. It's going to get used up. And of course, as it's getting used up, what's happening? What's being made? Water is being made. And that really should be a mirror of the other graph, right? I'm going to do my best to make it look like a mirror. But at a certain point, if I've got almost no hydrogen gas, well then, is that forward reaction going to happen very fast? If I've got almost no hydrogen, no oxygen, what's going to happen to that forward reaction? It's going to go as slow as it possibly can. Well, it's going as slow as it possibly can. What about this reaction? Because now our concentration of water is extremely high. It's going to speed up, which means we should actually expect to see some of that water get used up and turned into hydrogen and oxygen. Does that make sense? But of course now the concentration of hydrogen and oxygen is going up, and that's a much quicker reaction. So what's going to happen? It's going to start being used up. And this process is actually going to happen over and over again, but we would expect it to get steadier and steadier over time. Does that make sense? Until eventually so the fast reaction occurs quickly, but will eventually make enough H2O that the reverse occurs. This will cycle until both reactions are happening at the exact same rate. At this point, the concentrations will no longer change. I'll give you a minute to write that. And then we'll talk about it. I guess you need the text more than the picture right now. I'll zoom out after. Oh my goodness. Excuse me. Yeah.
You only write the rate. Is the K lowercase or uppercase?
Lowercase. Don't worry, we're coming up on uppercase K's. Tamari. You'll notice that I no longer say library or Tamari. It's a Simpsons quote. Sorry, not. And why would you know that? Is SpongeBob your generation's equivalent of like something that's constantly being quoted? I hope you won't take offense at my saying that Simpsons, at least early Simpsons, is a lot more clever than SpongeBob. What's your clever show? Because SpongeBob is more like a Looney Tunes type thing. Like, it's mostly ridiculous, though very charming.
Clever show.
Clever. Like, the jokes in The Simpsons are always like 11 layers deep. They're very clever. It's just a lot of cleverness that goes on. Like, just apropos of nothing, there's an episode where like Homer becomes Mr. Burns' personal assistant and eventually gets so frustrated with him that he punches him out and gets fired, and then Mr. Burns has to fend for himself, and then he at one point picks up the phone and says ahoy, and like that just seems like a weird little character beat, but actually the joke is that when Alexander Graham Bell first invented the telephone, he suggested that it would have its own greeting and that it was sort of a nautical thing, so they should use ahoy when answering the telephone. So the joke is that like Mr. Burns hasn't answered a telephone in so long, he still says ahoy when he answers it. Like, that's, nobody would know that. Like, why would you know that watching the show? But that's like, right? Like, there's just layers of kind of, it's a bunch of guys who went to Harvard who think they're smarter than you, so they're building like layers of humor into their jokes. I don't know. And then, I mean, by like season 9 or 10, it just got kind of dumb, and now it's, I think, sort of pretty disposable. But those first few seasons are pretty epic. SpongeBob, I find too frenetic for me. Like, it's got a little bit too, as an ADHD case, SpongeBob makes me feel like I'm going to like have an aneurysm. But, you know, not without its charm. It's like Bill Nye the Science Guy. When I was a supply teacher, it was in the Bill Nye era, and I was constantly playing Bill Nye videos, and I'm like, this is way too frenetic for me. I feel like I'm going to have a meltdown. I can't handle it. Anyway, okay. Can we talk about this? Does that kind of make sense? The big idea here is, at first, obviously, the fast reaction is going to win, right? Does that make sense? A, because we've got a ton of this stuff, and B, because it's a fast reaction, right? But eventually, you're going to use up so much of that stuff that's going to swing the other way. But because the other reaction is faster, it's going to take over, and they're going to go back and forth, and they're going to kind of fight, right? But if they keep doing that, eventually you reach a point where those two reactions end up with such perfect concentrations that the reaction happening forward is going at the exact same speed as the reaction happening backwards. And when that happens, these are both just going to look like a straight line. Because as fast as this line might be trying to go down because it's being used up, it's also getting made, so it's going up. So at a certain point, the concentrations will always appear to reach a constant state. That constant state is called an equilibrium state. Okay. Let's consider the simplest possible example. Two one-step reactions. Okay. And let's say that the first reaction is A reacts such that it gives us B. All right. And the second reaction is that B can react such that it gives us A. Okay? Is that cool? All right. And we're going to have these be one-step reactions, which means we can actually say that this one would be what? Rate would equal talk to me.
K.
Yeah.
A.
Concentration of A. And keep in mind that we know it's a single step reaction, right? So it's just going to be exponent of 1, right? Because in a single step reaction, we can just use these coefficients, right? And for this one here, the rate is going to be some other constant, constant 2, times the concentration of B. All right? All right, so if we start with if we start out with 1 molar of A and 0 molar of B, obviously what's going to happen at first? So as time goes on, yeah, I would love to. How's that? We're going to do the same thing here. We'll call red the concentration of A in molar, and we'll call blue the concentration of B in molar. So we're starting with 1 molar concentration of A and 0 molar concentration of B. Obviously, in the first reaction, what's going to start happening? A is going to get turned into B. So we don't know what this reaction looks like. Let's say it goes along and the A gets turned into B like this. Well, at the same time, B is getting turned into A. Does that make sense? And again, these should be a mirror of each other. I don't entirely trust my ability to do that. But how fast B gets turned into A depends on the concentration of B. So as the concentration of B goes up and up, it's going to want to get turned back into A. So these reactions are going to slow down. And in fact, they'll actually reverse for a while, such that we're actually producing more B than A. And they're going to do that same thing where they kind of oscillate back and forth until they reach a steady state. And these should mirror each other. I'm going to do my best to show that. How's that feel? Is that reasonably okay?
So the reactions don't keep on repeating.
I don't know what you mean by that.
Like,
Oh, I hate
it
that.
just doesn't turn into like a sine wave or something. I thought that was what it was supposed to be.
That's good thinking, actually. It doesn't turn into a sine wave because eventually, the truth is, it actually is. Ready for this? If we wanted to model this in Desmos, and I know you guys want to because I know how much you love your Desmos modeling, you advanced functioners, you. We could say that this is going to be, we'll go our concentration there, y equals sine x, right? And we'll have to do, are we in degrees or, what does Desmos default to? Degrees? Radians. Well, that's fine. So we just have to do plus pi over 2, and we'll be good, right? There we go. And then I'm going to give this a 0.5, and I'm going to put it plus 0.5. There we go. Okay? Now, like, I'm just arbitrarily picking these. But the question is, why don't they do this, right? Well, the answer is that, actually, that should be plus 1. And, like, whatever, I'm just trying to make these kind of separate. So it could look like that, except both of these are going to be times 1x, or e to the x. Oh, there we go. And let's just make that a 0.2. That'll do. I think you can find that does.
Oh, wait, actually, it does.
Thank you. Apology accepted.
I'm so sorry for everybody.
Me too. Yes, you will, but that's okay. I'm failing anyway. We'll come back to modeling it. Point being, it is a sine wave, but it's converging. It is converging on an asymptotic value. And you know about your horizontal asymptotes. And the reason it's converging on a horizontal asymptotic value is because, again, every time it responds a little bit slower. Yeah.
What's that word mean?
Asymptotic? Asymptotic just means it is approaching some value that it will never perfectly reach. In this case, it's always going to be slightly oscillating around it, but those oscillations are going to get so small that functionally it is just a set value. Does that kind of make sense? Theoretically, these are actually still, we're using up a little bit of A, then we're remaking it. Using up a bit, remaking it, using it. So it's ever so slightly oscillating, but it's happening so close in rate that eventually we reach a steady state. So this here, I got to change that. I can't handle that. I can't abide. There we go. This is the steady equilibrium state. Now, note, at the equilibrium point, or the equilibrium state, I should say, the concentration of each species is constant because the rate of the forward reaction, I guess I can just write the word forward, is equal, hence equilibrium, to the rate of the reverse reaction. What it doesn't mean is that the concentration of each species will be equal. Look here, if we look at our diagram, obviously the rate of these two the amount of A in this particular reaction happens to be greater than the amount of B when it reaches equilibrium. Does that make sense? So we'll make a note there. Which concentrations are higher and which are lower depends on the initial rate of each reaction. In other words, on the K value of each reaction. Does that make sense? If the forward reaction has a high K value, then the forward reaction is going to happen more, and you'll end up with a lot of the products of the forward reaction. If the reverse reaction is faster, you'll end up with a lot more of the products of the reverse reaction. Yeah. Is that a hand? On this point here? Okay, let's look. Good question. The initial. That's a great question. The initial rate, in other words, the K value. For example, let's look at three possibilities. Ready? If K1 is bigger than K2, that means A turns into B faster than B turns into A at first, right? In which case, you will end up with, if this is A, right, and that's B, we're actually going to end up with more B, because the reaction to make B starts out faster than the reaction to make A. Does that make sense? So even if we start out with lots of A, it's mostly going to get used up, and we'll end up down here, and the B will mostly get made, and it'll end up there. Does that make sense? On the other hand, if K1 is less than K2, in other words, if A making B is slower than B making A, even with the same setup, even starting with lots of A, that's going to slow down fairly quickly and just do its thing like that. One sec. And then what's the other possibility? They could be equal, right? And in that case, if K1 were equal to K2, if those reaction rates were the same, then we would expect that the concentrations would end up also being the same. We would expect this to steady out, and this to steady out, and them to kind of steady on the same line. Does that make sense? So what we end up with more of depends on which K is bigger. Did that answer your question? Actually, or are you just saying that to shut me up? Okay, good.
When they both eventually become steady, does that matter? Like, the values, do they matter then?
Yeah, because where they end up being steady is a function of which reaction can go faster than the other. Eventually, in other words, the only way to make look here, if K1 is faster, then the only way to make it steady is to make the stuff you need to make K1 happen be at low concentration. And the stuff you need to make the second reaction happen be in high concentration, and that's how you're going to make them equal out. Because the first reaction is a faster reaction, we're going to have to keep its concentrations low to make it match up with a slow reaction. Here we see the opposite. Because the first reaction is slower, now its concentrations have to stay higher so that it will steady out with the second reaction. And here, if the K values are exactly the same, then to get their rates to be the same, you'd need their concentrations to be the same. Does that make sense? It was a good question. Kartik, did that address your question, or do you still have one?
It's kind of more like a minor one. But
Okay.
the K values, if the K value is bigger, is it like slower or faster?
Yep. Yeah, a big K value means a fast reaction. A small K value equals a slow reaction. Yep, absolutely. That's right. If you look here, don't write this, or do. Actually, I mean, it doesn't hurt. We could say, recall, rate equals K times the concentration of X to some exponent X, Y to some exponent Y, whatever, right? But if K is big, the rate will be bigger, right? if K is small. You know what? I shouldn't use big arrows like that, because if K is large, rate is fast. If K is small, the rate is slow. And you'll never have a negative K value, right? That would imply that the reaction goes backwards. And then you think, well, didn't we just learn about that? But we would never define K as negative, because then we would go and say, let's talk about the other reaction. Does that make sense? So you'll never have a negative K value. It's always positive. But if it's large, it means you're talking about a fast reaction. If it's small, you're talking about a slow reaction. And no matter what, they don't have to be the same. There will come a point where the concentrations work out that the forward reaction and the reverse reaction will go at the same speed. That spot must exist. All right? So for any pair of forward and reverse reactions, there is a state where the rate forward equals the rate of the reverse, and we call that the equilibrium state. Now, obviously, you can already tell me what that will depend, what could change that equilibrium state, because you know what changes K values. What are some of the things that can change the K value of a reaction? That doesn't change the K value. It changes the rate. So you're right. If we change the concentrations, we'll change the equilibrium state. So yeah, I like it. Not by changing K, but by changing concentration. Yep. What else? Pressure. If we change the pressure in a system, K changes, which would change where the equilibrium state's going to live. But you'll still have an equilibrium state. It'll just be at a different set of concentrations. What else could change the equilibrium state? What else affects K? Temperature. Good. If we increase temperature, that results in things bouncing around more, reactions go faster. That's going to change your K values, so that's going to change your equilibrium state. Surface area, catalyst, right? If we add a catalyst, if we change the activation energy, things like that. Does that kind of make sense? Yeah.
You know how you talked about the Earth's water?
Yeah.
Are they both equal, or is one higher than the other?
So they've reached a steady state. Don't draw this. But on Earth, we have concentrations of water and we have concentrations of hydrogen, right? And the concentration of water turning into hydrogen, in fact, we started out with a lot of hydrogen on planet Earth, right? And not a lot of water. Very quickly, as our Earth evolved, most of that hydrogen, because we had oxygen, ended up turning into water. And then some of that hydrogen still gets made. There is hydrogen on our planet, right? We can go find it. And in the meantime, it's almost all been turned into water. And that is the steady state on that, right? Our planet has a lot of water on it, and it has very little hydrogen on it. But it does have some. Did that answer your question? And obviously, the concentration of oxygen is interesting because it has found its own steady state down here. In other words, there's no guarantee once you have three reactants, there's no guarantee that the one reactant's going to be the same as the other, right? We have lots of oxygen on Earth, not nearly as much as we have water, but a lot more than we have hydrogen. But still, it's reached its own steady state. Did that answer your question? Okay, cool.
Does the oxygen get affected by the other two, or no?
Sure, yeah. Now, there's way more things involving oxygen than just that. So that reaction is not going to be the main thing that drives how much oxygen we have on our planet, but it's one of the things driving that. Because the actual equilibrium, you have to consider every possible reaction that oxygen's involved in the world, which is billions of reactions, right? Oxygen can react with magnesium that it finds on Earth. It can react with iron. It can react with hydrogen. It can react with carbon. Oxygen reacts with everything. Oxygen gets around. So it's a bad one to kind of pick as an example for this because it's so ubiquitous. Which is why we are going to quickly just say in part C here, even though I didn't do a part A or a part B, though I meant to. That's okay. We're now in part C of the note. we're going to consider the math of it. Of our simple example. And we'll quickly just remind ourselves what our simple example was. It was A turning into B and B turning back into A, right? Very, very simple example. We said A could turn into B, and we said in that case, the rate of that reaction will always be equal to some constant K1 times the concentration of A, right? And in this case, because it's a one step, it'll be A to the exponent 1, right? So we're just going to do that, right? And reaction 2 was that B can turn itself back into A, and the rate of that reaction will be what? And we'll call this rate 1 and rate 2, I guess, as well. K2 is equal to the concentration of B, right? And again, it's just going to be to the exponent 1 in this particular case because it's only the coefficient is 1, right? Remember, in a single step reaction, if the coefficient here were 2, you could just square that. If the coefficient were 3, we could cube it, right? That's only true in a single step reaction, right? But now, at equilibrium, what is true about this? At equilibrium, rate 1 is equal to rate 2. Right? That's our steady state. Oh, fun spelling of steady without an A. So, in that case, what can we say? Two things that are equal to the same thing are equal to each other. In this case, rate 1 is equal to rate 2. So, what can we say? Therefore, K1 times the concentration of A must equal K2 times the concentration of B. Rate disappears from this completely, right? But we can say there's a relationship between the two concentrations. If we put constants on one side and concentrations on right, how would that look? Sorry? We would say K1 over K2 is equal to concentration of B divided by the concentration of A. In other words, at equilibrium, there will be a specific ratio of the concentration of B to the concentration of A that will be consistent. Does that make sense? And then the last thing we can do is, let's combine our constants into a single constant. Does not mean the constants are equal. If it did, this would always equal 1, but it doesn't. Remember, the K values are going to determine where those two rates end up being equal. They could be the same. I've never heard of a reaction where the forward and the reverse have the exact same K value, but it's surely theoretically possible. But in practice, they're going to be different, which means this is going to have an actual value. Does that make sense? And if we combine these into a single constant, we now use an uppercase K, and we call it the equilibrium constant. And we say the equilibrium constant is the concentration of B divided by the concentration of A in this case. How's that feel? That's right. So, and you'll sometimes see Kc, you'll also see Kc, you'll see Ka for an acid, KB, KEQ, KSP, etc. Thing to know, uppercase K equals equilibrium constant.
We don't have a part. So you're gonna have to ask.
Does that make sense? So the A would be if we're talking about an acid reaction. The B would be if we're talking about a base reaction. C is sometimes used just generically. They talk about the Kc of something. ASP is for solubility. EQ is used generically as well. Regardless of what you say, if you see an uppercase K, it's an equilibrium constant. The subscript is just for keeping track. Does that make sense? You can kind of make the subscript whatever you want. Usually it's the type of reaction. Does that make sense? Feel okay? All right. Tomorrow we're going to actually look at writing these equilibrium equations for more complex reactions. But the nice thing is this. This is actually relatively easy. Can I try writing something and don't necessarily write it until maybe if it's good we'll write it. And if it's not, we'll just use it illustratively. Is that fair? Pencils down? All right. So this, I guess, would be part 4. All right. Was I doing letters? Part 4 it is. Multi-step reactions. And this is actually nice as opposed to being hard. This is a case where it gets easier. For equilibrium, and again, don't write this yet. We'll see if we want to, because I do have a note on it tomorrow, but I'm just feeling like we have time right now, and you guys actually seem to be grasping this. So let's see. For equilibrium reactions, we can ignore intermediate steps. Unlike rate equations. Can I make sure I have your attention here? All right, thank you. So, unlike rate equations, we can ignore intermediate steps and use the subscripts directly. Not subscripts, right, the coefficients directly. Here's why. Okay, ready to get a little bit into the weeds here? All right? Can you put up with me here? Let's try this, okay? Let's say we have a reaction where 2A plus B yields C. Is that fair? Okay? And let's say, therefore, that the reverse reaction, that would be the forward reaction, right? And the reverse would therefore be what? I'm going to line those up differently here. The forward reaction would be 2A plus B gives us C, right? And the reverse, obviously, then would be that C can be broken down into 2A and B, right? Okay, now, let's say this actually follows 3 steps. Three-step reaction. Let's say in step 1, 2A forms an A2 complex. Is that fair? Actually, we'll just do a 2-step reaction. Why the heck would I do 3? Let's just keep life easy. Okay, so that's step 1. And then in step 2, A2 reacts with B to give us C. Is that fair?
Wouldn't
Okay.
it be like the first step would be A plus A.
Yeah, if you prefer that, A plus A yields A2. That's fine. That's the same thing as saying 2 A's, right? We're just collecting like terms, but if you like that better, do you like that better? Let's do that. That means in reverse, first what would happen is that C would break down into A2 and B, and then what would happen next? A2 would break down into A plus A. All right? So this is also 2 steps, right? Which makes sense because it's the reverse 2 steps. Is that fair? Okay. Now, the rate of this one would actually be K1 times the concentration of A squared. Is everyone comfortable with that? Does that feel okay? The rate of this one would be K2 times the concentration of A2 and B. Oh my God. But okay. That's all right, right? Okay. Over here, the rate of this one, again, don't write this because this is probably going to be not the cleanest way to do this, but I just want you to see there's a mathematical backdrop to this. We could call this K3, right? And it would be equal to the concentration of C, right? Is that cool? Concentration of C, exponent 1. And the rate of this one would be K4, and it would just be equal to the concentration of A2. Right, is that fair? Now, ready to do a little math wizardry? We're just going to multiply these together, and we're going to multiply these together. There's nothing saying you can't do that. Is that fair? So that would be at equilibrium. Keep in mind, all rates must be the same, right? All the rates are equal. If you want to, we could call this the rate at equilibrium, the rate at equilibrium, the rate at equilibrium, the rate at equilibrium. Is that fair? Okay, so let's just multiply these together. What's rate times rate? That would just be rate at equilibrium squared, right? K1 times K2, we'll just call it K1, K2. Doesn't matter, right? And what do we have here? We have the concentration of A squared times the concentration of A2 times the concentration of B. Is that cool? We just multiplied these together. K times K2 is K1, K2. A squared, there's no like terms, so you just multiply it by A2, you just multiply it by B. All right? This one over here would be the rate at equilibrium squared, and that would equal K3, K4 times the concentration of C times the concentration of A2. Now, these two things are equal. And if they're equal, what can you do? Yeah, we can just set them equal to each other. So we can say K1, K2, A squared times A2 times B is equal to K3, K4 times concentration of C times concentration of A2. And then we'll do the same trick as last time, which is constants on the left, everything else on the right, right? And that would give us K1, K2 over K3, K4 being equal to concentration of C divided by the concentration of A2 divided by the concentration of A squared times concentration of A2 times concentration of B. And of course, what cancels? Those cancel. And we'll combine these constants. We'll just say capital KEQ is equal to the concentration of C divided by the concentration of A squared divided by the concentration of B. Now listen, I will never ask you to reproduce that. All right? But do you see how the intermediate steps end up canceling out? And this just ends up being what you would have gotten if you just treated it like a one-step reaction. All of this math is just to show that when we're dealing, because we end up setting them all equal, we can ignore any intermediate steps. Rate laws are actually way harder to work with than this. With rate laws, we had to do the whole experimental thing, right? Where you had to double this, see what happens, double that, see what happens. You don't have to do any of that with equilibrium constants. The big takeaway is just that, and maybe this is the only part you need to write, though if you want to show the math, it's not bad, but if it's going to confuse you, don't worry about it. This is the thing you can know. For equilibrium reactions, we can ignore intermediate steps, unlike rate equations, and we can just use the coefficients as exponents. And so it ends up being that for the reaction of A, 2A plus B yields C, and C yields 2A plus B, we end up with an equilibrium statement that is the concentration of C divided by the concentration of A, take that exponent, square it, concentration of B. And we'll talk about why we put products on the top and reactants on the bottom. Wouldn't actually matter, you could do it either way. That's a convention, but it's how we do it. Sorry? Do you want the math?
No, just the top part.
Just the wording. How's
For
that?
equilibrium reactions.
Now again, that little mathematical proof, it's not a full proof. A full proof would involve showing that no matter what the intermediate steps are, it cancels. But you're just going to have to trust me that no matter what you make the intermediate steps, you can make them 72 steps. You'll end up with rate to the exponent 72 on the left and rate to the exponent 72 on the right and all kinds of gobbledygook, but everything's going to cancel out, and you'll end up with just the overall reaction. Again, all of this you will never need to know. But if you like to know mathematically why something works, that mathematically is why this works. Does that kind of make sense? Yeah. All right. You guys have got a bit of time. You can use it as you see fit. Please be productive. If you want to see how you did on your test, feel free to come up and take a look. Like I said, I can't give those back to you until everybody is written. But I would be delighted to show you. I just have to go grab them from the back.
Okay. That's fine.
Fine. All right, step on up. Kartik, were you first?
I was first, actually.
All right, perfect.
Yeah, and that's what I
I'm going to stop recording so I'm not streaming everyone your grade.